Hey, good evening, everybody. Thanks for coming out and welcome. My name is Dave Swartz. I'm the president of the WWV Amateur Radio Club. And I'd like to welcome you to the Otterbox Digital Dome Theater at the Fort Collins Museum of Discovery. That's where we are tonight. Tonight, we're pleased to have two presentations that highlight a unique and special radio station that's the focus of our Amateur Radio Club. I was 8 years old when I first heard WWV on a shortwave radio. And I tuned around, and there it was again. And this time it was even louder than the place it had been on the dial before. And as an 8-year-old, questions pop in your mind. Why was it always on the exact number? Other stations weren't. What's that ticking sound every second? 8-year-olds ask a lot of questions. So you listen for a minute and you know the time. You'll listen longer and the beat kind of gets to you. The stories we've been told by folks who have listened for a lifetime are amazing, and you soon realize this station has a devoted following. Its importance as a technological tool can't be ignored, but neither can its importance as a cultural tool as well. Tonight's program is hopefully streaming live via YouTube on the Northern Colorado Amateur Radio Club channel. So if you're out there, you want to find us, go to youtube.com/NCARC and click on the live tab and you're there. And I guess if people are already tuned into it, they're picking this up. The program will be edited and posted later as well, so we'll add a little bit to it. And we'll take a break about 10 minutes between presentations this evening. So our first presenter this evening is Mr. Glenn Nelson. Glenn has been an electronics technician at radio stations WWV and WWVB in Fort Collins since 1997. He has worked with the military and government broadcast systems for 38 years, and he holds amateur radio license Alpha Echo Zero Golf Foxtrot, AE0GF. It's been a pleasure to get to know Glenn and his son Jonathan over the last 4 years. So would you please welcome Mr. Glenn Nelson.
Dave, I think you have my notes. Well, thank you, everybody. Welcome. It's great to be here tonight. And we're going to wait. We're going to listen to this for just a few more seconds, and then we'll know what time it is.
At the tone, 0 hours, 17 minutes, coordinated universal time.
There it is. Okay, that's our presentation. No, I'm teasing. All right. It is good to be here, folks, with you in this amazing space. Never had the privilege of seeing or the chance to see a presentation here. This is really cool. So I'd like to turn on the presentation now, if I could. All right, good. Thank you. No problem. So the sound you heard was, of course, WWV. And tonight we are celebrating 100 years of what you just heard, which are frequency broadcasts from standard frequency broadcasts from WWV. We'll talk more about that in a minute here. We are located up by, I guess, about halfway between Fort Collins and Wellington. And if you've ever been out that way at night, you might have seen something like this. And I'm so glad this picture is up here tonight because I forgot to take a picture. I meant to do this of our tower lights at night. But if you're between Wellington, Fort Collins on I-25 and you look over to the west, you'll see our antenna arrays. We've got 8 400-foot towers, and we've got that's for WWVB, our 60 kilohertz frequency service, and then we have our shorter towers for WWV, and those we'll be talking more about those in a moment. So something I've seen folks do at a gathering like this is to figure out who came the farthest to be here tonight. I know some folks are here from the Cleveland area. Is anybody here from farther away than Cleveland? Boston. Very good. My wife is from Massachusetts. Anybody else? Looks like Boston might take it. I'm not sure that we have a prize for you, but we're glad you're here. How many of you folks have heard of WWV before? No. Is there anyone here who has not heard of WWV before, who just kind of wandered in or just happened to see this announcement and said, "Hey, what's this all about?" Yeah? One or two people, perhaps? Excellent. We're glad you're here. Happy to share. How's it going back there? Anybody have any jokes? We can.
Jokes.
No jokes.
Jokes
No,
are
like,
horrible.
Yeah, my jokes are horrible. You know that. You know that for sure.
Of course, it's a show about technology, and that's why it's not working, right? So
Yeah. So where were you when you heard that WWV signal the first time?
That's really funny. I was visiting my future ex-brother-in-law. Put that together, okay. But he was going to Yale, and so was my sister.
Cool.
And I was 8 years old, and big gap between me and my sister. And so I happened to be there. He was from England, and he had a beautiful Grundig shortwave radio. And I was playing with it and tuning around, and sure enough, you're tuning around, and it's beeping away, and it's like, that's weird. And
is that one of those
moved over.
streamline radios?
No, it was a big one. I mean, it had the dial that you could turn, and it kept turning, type of thing. So it was a very nice radio.
Oh, you
and
spin
and I was tuning around, and I just kept hearing that, and I was just like fascinated, and I really did think, why is this important? Why are they doing this? And got me started to get interested in science, and I think it was pretty cool. Radio to hear, I got interested. My mom and dad decided, oh, maybe we should get our kid a Heath kit and start putting electronics together. So we did that. I did that, and sure enough, by the time I was about 12 years old, I had a nice shortwave radio, SW717 from Heath kit, and it had a BFO, which is really important because then I could hear the sidebands. And so I started tuning into the...
What is a BFO?
Beat frequency oscillator. So it interjects a signal and lets you suppress one of the sidebands. So it was really cool. Hey!
All right. Thank you.
All right. I'm going to sneak out. Thanks.
Marvelous. Thanks, Dave. All right, so here we are. Yes, I'm Glenn Nelson, AE0GF. That's my amateur radio call sign, but I suppose another call sign is WWV. So here we are. What is WWV? Most of you know this already, but we are a time and frequency broadcast of I actually didn't realize I was not going to be able to see the slides. That's interesting. All right, so there we are. We broadcast the time of day, standard time intervals, and standard frequencies and other information from Fort Collins, Colorado. We actually operate on 6 frequencies, 2.5, 5, 10, 15, 20, and 25 megahertz. And our mission is to, well, you see it right there, disseminate time and frequency, standards, and so forth. So let's go the other direction here. All right, so what is NIST? NIST is we are part of the U.S. Department of Commerce. We are the National Institute of Standards and Technology, and you can see the mission statement there. That's off of our website, but for the purposes of our discussion tonight, the part of NIST's mission we'll be focusing on is maintaining standards of weights and measures for the U.S., a couple of those standards in particular. So when you think of early radio, we're going to be talking about early radio history tonight. When you think about early radio, when I think about it, the first thing that pops in my mind is something like this. This would be a cathedral, was called a cathedral style radio from the 1930s. You might imagine our grandparents or great grandparents gathered around listening in the living room or whatever. But when we go back far enough, actually listening to an early radio signal would have looked more like this. This gentleman has his headphones on. He is copying Morse code. He hears it over his headphones, and he's writing down the dots and dashes. And that is really what radio was about from its very beginnings up until the 1920s, the early 1920s. It was more of, in fact, it was almost all a means of communicating between two or more parties. Radio stations and antennas were huge, expensive facilities that were owned by large corporations or national agencies. Morse code messages could be sent long distances but were costly. The idea of sending the human voice or music over radio waves was a novelty. And this photo shows this is an early radio telegraph radio station in Canada. But radio telegraph messages did reach some level of sophistication. This what you see here is a paper tape that was recorded using a type of strip chart recorder, a pen that would go back and forth as the paper traveled under it. And what looks like a kind of a pulse stream up there is actually dots and dashes, or dits and das as we say. And the radio operator received this message in New York in 1920. It was sent from Germany, and he decoded it, and those dits and das spelled Berlin urgent. But now we're going to take a shift here in our story to the Bureau of Standards. The National Bureau of Standards is the predecessor of NIST. It was founded in 1901 to establish and maintain standards of weights and measures for the nation. Prior to this time, there was no national agency or group doing this for commerce and industry. Did you know there were at this time at least 8 different gallon measurements and 4 different feet in use in the U.S.? There was somebody had to say what a pound was, what a gallon was, and what a foot was. And so the Bureau of Standards was founded in 1901. The first location was off of Connecticut Avenue in Washington, D.C. And it didn't take long for the Bureau to get into what was called wireless, sometimes called wireless research. The first radio research conducted by Dr. Louis Austin got right to work developing a test instrument, a detector for very small alternating currents and electrical waves. And he published a paper about his work in 1905. The radio research gained such importance that a separate section was founded, the Radio Laboratory Section, in 1913, with a staff devoted to radio research. Early work for the radio section involved a radio navigation system for ships at sea and for use when fog limited visibility. And then World War I came along. And when that war broke out, or when the U.S. Declared war in 1917, all private and commercial radio signal transmissions and reception were prohibited. So the radio section switched gears and worked on war-related projects, including the first underwater communication by radio with U.S. Navy submarines. And further contributions also during the war, an early form of aerial radio navigation was developed. Textbooks on radio theory were written for military training. And research involving vacuum tubes was carried out. Vacuum tubes were a recent development, and this was very important. Because they allowed the transmission and receptions of sounds, including music and the human voice, rather than just dits and das of Morse code. So after the war, the potential for radio vacuum tube or vacuum tube technology was explored further at the radio station. This newspaper article here describes a demonstration at the Bureau of Standards facilities there in Washington, D.C. And this popular song, Pretty Baby, a big hit in the day, was played on a phonograph, a record player, fed to a transmitter, and broadcast several hundred yards to a receiver in an auditorium where people were assembled, and they were astounded. And what's really cool is you can listen to that song on YouTube today. WWV's call sign was granted in October 1st, on October 1st of 1919. And you can see down here in the lower right, there it is, and it was listed as experimental. And we actually celebrated the 100th anniversary of this event 4 years ago at the station, and we'll talk more about that later. But the experimental radio station was really a collection of homemade and military surplus equipment located in this laboratory, or one like it, connected to an antenna. But this is the source of WWV's first broadcasts. Previously, radio stations existed primarily, like we said, for point-to-point communications. But the idea of one station sending a signal to many listeners, broadcasting, was just then being considered. So this state-of-the-art audio broadcasting system used a military transmitter, a telephone microphone with that big horn-shaped horn, really, is what it is, just pointed at the speaker of a Victrola, a wind-up record player. And so the first experiments used this setup, apparently, or something like it, to test the range of audio broadcasts. And I thought it was really interesting as I was doing the research for this, for these talks. The articles and the news releases of those days just convey a real sense of excitement about the new technology. This is the story in a Washington newspaper from February of 1920 of a guy sitting in his house, and he's listening in on, it says, general wireless messages, meaning Morse code, just to see what's out there, when he heard a human voice saying, "Hello there," and it made the newspaper. But the Bureau of Standards was conducting experimental broadcasts several miles away, and he heard that. So it's really cool to read about how excited people were. So in the spring of 1920, the Bureau of Standards started our first scheduled broadcasts. A person we call a DJ today would go in the evening and spin records, play classical music usually, on the air for WWV, from WWV, and it was to test for range and usability of the signals. And 40 kilometers is about 25 miles when they first started this scheduled broadcast. Not only was MBS doing research on its own signals, it was also working with radio amateurs around the country to learn more about the effects of signal range, fading, and atmospheric noise. And I think this research is especially notable because it's still going on today with some exciting developments, as you'll hear from these folks in our next presentation. So other work the radio section did included an early portable receiver. Isn't that amazing? It was cutting edge at the time. It's called a portaphone. Also, this was actually quite helpful to a lot of folks here. This is the first radio receiver powered by normal house current, they called it, 120 volts AC. Up until then, all radios were powered by batteries. You can actually see the power cord connected to a lamp socket. Don't recommend trying that at home. So in the early 1920s, there was so much interest in radio technology and broadcasting, in receiving these signals that were out there on the air, that the Bureau of Standards actually started developing letter circulars that would include kits or not kits, but plans to build your own receiver at home. And the government had lifted the ban on commercial and private radio use in October of 1919, and this radio just exploded in popularity. The massive increase in numbers of commercial and amateur radio stations on the air did have problems, though it did bring problems. There was a tremendous problem with interference. And the problem was so bad. Well, imagine turning on your radio in the 1920s, and this thing you spent a lot of money for, and you turn it on, you're expecting to hear your favorite program or music or news, and your signal is being drowned out by another station. Not just noise or static, but other stations. Those numbers that we see on our radio dials, that's what Dave was talking about earlier, they indicate on which frequency that station is supposed to be operating. But in those days, it was truly not an exact science. In the early 1920s, radio theory was much less well understood. The study of wavelengths and frequencies of radio waves was young, and the equipment for calibrating station transmitters was primitive. The stations had difficulty keeping their broadcast equipment on its assigned frequency. And news reports of the era show that this was one of the few times in which every interested party in this debate, from broadcasters to amateurs to the listening public, they all agreed that the government needed to do something. And so the Bureau of Standards did something. In March 6th, actually, 1923, WWV began broadcasting standard frequencies. These frequencies were accurate to the highest standards of that time and allowed other stations to tune their equipment to the broadcast and calibrate the transmitters so that they would be on their assigned frequencies. And this is what we're celebrating this weekend here at the museum, 100 years of standard frequency broadcasting. The station would wrap up the programming for the day, and then at 11 p.m. or afterwards, the engineer or a technician would tune a receiver into the WWV, one of those frequency broadcasts. Then the technician would calibrate the station equipment to operate at their assigned frequency compared to this known frequency standard. And we can see the frequencies that were broadcast there. Twice a month. Here's a view of the original WWV antennas in Washington. They were right over the radio section laboratory there. There were other frequency stations as well. Since WWV could not reliably reach the western part of the U.S., other stations took up the effort and established ways to compare their signals with WWV for accuracy. This slide is from 1938. They were still going on then, but earlier examples included a radio station, a college station at Stanford University, and the radio station operated by the Gold Medal Flour Company in Minnesota. So in the 1930s, as time went on, WWV began to take on more importance to the broadcast industry. It enabled radio stations to comply with federal rules regarding their allocations. And so it was moved to its own facility in suburban Maryland. This is about 15 or 20 kilometers from the Bureau of Standards. The antennas in this photo are accentuated or retouched to help us see them. By 1930, crystal oscillators had become the frequency standards in use at WWV, and accuracy and stability of the frequency broadcast increased dramatically. During this period, standard audio frequencies were added, including a 440 hertz tone, which is the musical note, A above middle C. This tone was used by musicians to calibrate their tuning instruments, still broadcast today. But in 1940, disaster happened. A fire consumed the radio station in November of that year. But WWV was back on the air in a short time at 5 megahertz. And at that time, it was decided to actually create or to put WWV on the air continuously. Up until that time, it had been a weekly schedule of certain frequencies on the air at certain times. But probably the most interesting thing to us today is that seconds pulses were synchronized with the U.S. Naval Observatory for the first time. And so that's important. USNO was responsible for disseminating time of day information to the public at that time. That was their charge. But if you have a reliable frequency standard, it's easy to make a clock. And so we'll talk more about that in a moment. So our station was so important that Congress allocated a whole bunch of money at that time to build a new facility a few miles away in what is now known as Greenbelt, Maryland. And it was completed in 1943, I believe it was. So we're on the air there with, we have, let's see here, I'm losing my place. Yeah. Right, our new transmitters and the frequencies that you can see there. And throughout the war at that time, eventually in 1944, the U.S. Naval Observatory granted permission to NBS to broadcast the official time of day. And this was a big deal for NBS at that time. The USNO transferred that responsibility for civilian use to the National Bureau of Standards. And USNO still maintains frequency and time standards for military use, including for GPS satellites. So if you folks are carrying a radio in your pocket like I am, the time you see here is going to be coming from a GPS satellite, traced to a GPS satellite. So in the 1940s and into the 1950s, a reliable time and frequency station was needed to serve American interests in the Pacific, and WWVH was founded in 1948 to meet those needs. The Boulder laboratories of NBS, including the successor to the radio station, those stations were moved to Boulder in 1954. In fact, the main building in the Boulder laboratories, if you've ever been down there, was called the Radio Building for many years. In the 1960s, WWV had reached its peak in popularity. We had industry, commerce, research, military uses, but the limitations were starting to become apparent. The limitations of HF signals for time and frequency standards have become well known. HF signals propagate in two ways: surface wave or ground wave, and skywave or skip. Skywave signals travel for thousands of miles. We've received reception reports from the South Pole for WWV. But when the signal bounces off the ionosphere, which is a layer very high in our atmosphere that responds to radio waves, the accuracy of the time and stability of the frequency is affected. Not enough for the user setting a clock or watch to notice. For extremely accurate measurements, it's a problem. And by the 1960s, more stable time and frequency references were needed. Let's see here. WWV were properties at those lower frequencies. It's different than an HF or shortwave. Is that the effective ionosphere is less reflecting or more of a duct. So the signal can follow this sort of duct for great distances. The frequency stability much greater than the HF signals of WWV. The 2026 WWV signal was discontinued in 1972, but its conversion to WWV at 60 kilohertz, and after several upgrades, it today provides the signal for millions of radio-controlled clocks. And perhaps some of you have seen those in Walmart or Costco or someplace, or they call them smart clocks. But they're receivers. They pick up our signal and they set themselves to it from WWVB. Okay, I am working my way to the next slide. There it is. So of the signals at times. The problem of location of the heavily used WWV signals was solved in 1966 when WWV was relocated from Maryland to the WWV site near Fort Collins. And also the new station would be much closer to the Boulder laboratories. This is a view inside the transmitter room when it was brand new, and we still maintain all of those specifications today, frequencies, power levels. So WWV actually created a tourist attraction for Fort Collins. We don't know who these ladies are. They're very interested in WWV. If you know who they are, let me know. It'd be really cool to know those folks. I found this photo in the National Archives in Broomfield. We think this kiosk was somewhere just north of where we are right now, right off of 287. If you look at that, well, this is not a pointer. If you look at that map, you'll see it says, "You are here." And in any case, the sign talks about tours, which are given weekly in those days, and not the case anymore, but our website has tons of information about the stations. But we were broadcasting our address, we still do, our address and our location twice an hour, and people came to see us, and they still do. So where exactly is WWV? Perhaps some of you are wondering. I have a feeling some of you already know this, but we're about halfway between Fort Collins and Wellington off of Highway 1. We talked about those tower lights that you can see at night. So in the 1980s, NBS became NIST, and the atomic clock, the main atomic clock, the National Standard of Time and Frequency, is maintained in Boulder, and its output is referred to as UTC NIST. Cesium oscillators are used now instead of quartz crystals oscillators. as the frequency standards at WWV, and they're synchronized using GPS common view techniques. This is a fairly recent view of our building, and I'm going to actually have to turn this thing around because this is where my notes end. And I'm going to have to actually look at this with you. Okay. You know, that might be a good idea. Really cool to sit down. All right. Whoa. Okay. All right. Front row. Nice. So for the hams and the radio geeks in the audience here, we're going to take a tour of WWV photo tour. This is our part of our time scale that we have right now. This is the local time and frequency reference that we use at the station, and this system is compared continuously with UTC NIST in Boulder. Here's our screen room. We have time code generators and monitoring and distribution equipment here. These time code generators create the audio broadcasts that we send out, ticks, tones, and time codes, and that you may have heard when we started our presentation. Our audio announcements, and we have 3 identical units to ensure correct outputs. Those 3 all output exact same information continuously, and we have systems that monitor that, and if any one of them starts to change or look different, it is taken offline. Our transmitters, we have 2 types right now. This is the ones on the left here. That's called a CCA transmitter. It's a manufacturer. Plate modulated 10 kilowatts output. That's our 5, 10, and 15 megahertz broadcast. And on the right, the Collins 8151A. This transmitter is actually was formerly a U.S. Navy piece of equipment. We have a number of these. And one of our technicians, when he was in the Navy, actually worked on these. And so he's very familiar with these. He was instrumental in getting these for us from the Navy when they accessed them. Each transmitter has each WWV frequency except 25 megahertz. It has a standby transmitter that starts automatically if the main drops, if the output power goes down, but we are still on the air if we have an outage with the main transmitter, and that happens automatically. Each antenna is fed by hollow coaxial transmission lines. I say it's hollow. It has an outer conductor and an inner conductor. The inner conductor is insulated from the outer. The outer is grounded. The longest run is just under 1,000 feet, and the total length is, as you see there, well over 4,000 feet. We keep these transmission lines pressurized with dehydrated air. Our antennas, all of our main antennas are halfway center-fed vertical dipoles. Here's an example. I believe that's going to be our 20 megahertz tower. It looks like it's leaning from where I am, but I don't think that's really true. There are tuning stubs at the base of each tower, and each of our towers is an omnidirectional radiation pattern. We have 2 broadband monopole antennas that can operate at any frequency that we broadcast, and therefore standby operation if we need to work on the main antenna. So whose voice is that anyway? From the 1950s to 1990, the announcer for WWV was Don Elliott Heald, and he worked for a company called Autocron Corporation. So would it be possible to play that sound? Let's see if this works. Yes, this was recorded in 1958.
National Bureau of Standards, WWV. When the tone returns, Eastern Standard Time is 2:20 p.m. p.m.
Very cool. So what you heard there was you heard the station ID, and you heard the time of day announced in obviously in voice, but you also heard Morse code. In those days, WWV broadcast our station ID and the time of day in Morse code. I found that, was able to find that recording in the National Archives, and that was actually in Beltsville. This was, or in the National Archives in Washington, D.C. But this recording was made for a Voice of America broadcast, a news item, a news piece for the Voice of America in 1958. But that is Don Elliott Heald, and he was on the air. His voice, that is, was recorded and on the air up until 1990 when we got our new... Now, I did not mean to do that. Okay, there we go. We got our new time code generators, and this is the gentleman that you heard when we first started our presentation tonight. His name is John Doyle. And as you can see, I took that picture in 2020 on January 16th at 19:04 and 48 seconds. There I go again. How about that?
At the tone, 19 hours, 5 minutes, coordinated universal time.
So that is John Doyle's voice. So QSL cards. QSL cards are, QSL means verification of reception. And over the years, ham radio operators and interested listeners have requested cards from us when they send us the information that verifies that they actually heard one of our signals. And these are examples of cards that we've sent out over the years. In fact, this image is a card. It is the 100th anniversary of our licensing, or our call letters, in October of 2019. Speaking of that anniversary, we actually had a cake. Andrew Novick, you can thank him for this cake. His friend did a beautiful job on this back in October of 2019. A special event station was organized by guess who? It was Dave Swartz, and the NCARC put this on and had a great turnout. Some of you might recognize this fellow here. And in Fort Collins here at the station, they set up, operated for a weekend. This 5 days. Okay, thank you. Yes, this young man on the right here is my son, who's working with one of the NCARC members there. So, WWV today, we have the local time scale that we saw was installed in 2005. We also, that time scale is used for internet time servers, so you can set your computer's clock using that system. There's also WWV by telephone at the number that you see there. We have military and scientific users, as we'll hear from the scientific community shortly here. Tons of amateurs and the general public want to know the time at the tone. So that concludes my presentation, but just want to say big thanks to Dave Swartz. Dave is probably WWV's biggest fan, if you haven't guessed already. This event that you're at tonight, and then the things that are going on this weekend, was 100% his idea, and he loves radio, and he cares deeply for WWV and our mission, and we appreciate it. So thank you, Dave.
So we'd love to take some questions from the audience if anybody has anything. I've got a microphone. I'm going to hand it to you if I can find you. Oh, okay.
Sure.
Hi, Glenn.
Hi there.
This is Leslie. I work here at the museum, so I'm not just I'm kind of a random person because I don't know a lot about this yet, but now I know a lot more, so thank you so much. This was amazing. But I did want to say, I looked up on the old newspapers and found out the names of those ladies who are standing at the sign.
No kidding.
Yes.
That is amazing.
So I'm the archivist here. That is what I do.
Wow.
So they are, oh, wow, cool. Applause. That was neat. So they were Mrs. Elsie Cox of Fort Collins, of the Fort Collins Chamber of Commerce. And hang on, I have to see here. And Bertha Ball, her sister,
There you go.
from Louisiana.
That's amazing.
Yes.
Thank you.
So
Thank
there
for
you
doing
go.
that.
So now we can add some metadata to that.
Absolutely.
That photo.
And Leslie is going to get her amateur radio license again. You used to have it, right?
I did. It was KB0KQG.
Awesome. She'll be back. Any questions for Glenn?
Yeah, Glenn, I'm just curious, are the feed line lengths managed?
Are they managed? They are static. They are fixed. We do have tuning stubs at the base of each of those antennas, but they basically were set once for maximum efficiency and haven't been touched in many years. Unless there's a leak or an air leak, that is, or a problem with the transmission line, it's been very stable.
Questions in here?
GPS kind of put Loran out of business for a position. What's the state of GPS in WWV as far as frequency and time?
Well, we use GPS as a common view in our common view technique for comparing the time scales in Fort Collins to the time scale in Boulder, and we don't actually use the GPS frequency reference. We just use it as a common point of reference so that we can see the same, so that both of our clocks can be measured at the same instant. And so that's how we use GPS, if that makes sense. It's called the common view technique. And that's an interesting question. I think that there's always going to be questions about, and it's a valid question about that. Should we should examine our scientific assets and make sure that their taxpayer money is being spent wisely. But I think what we found is that WWV is used in ways that we don't realize. There was talk from Congress of the funding for the stations not being available a few years ago in the following year's budget. That did not happen. But the news got out, and we got calls from all kinds of folks. I remember taking a call from a U.S. Navy electronics technician who worked on submarines. Are you guys shutting down? Well, we don't have any information about that right now. We don't believe that's going to happen, but it has been discussed. And by the way, what do you use our frequency for? I can't tell you. But it's one of those things I think that folks have taken for granted that will be there. But also, as we're going to hear shortly, there's a lot of new and exciting, I think, scientific uses for frequency references that were on the air continuously. They're powerful, and they are exactly on time and exactly within frequency specifications. And so I don't know if that answers your question. That's my personal opinion on it.
All right, yeah, maybe you mentioned it earlier in your talk, that when you showed these postcards, like these reception or receiving postcards.
QSL cards, yes.
QSL cards. I was curious, like, given the wavelength and the power, you can probably receive the signal far, far away. Like, is there like a record for where people have received it? I don't know, Europe?
It is, we figured out, my supervisor is here, and he figured out that is it the antipodal point, Matt, I believe, which is as far away as you can get from WWV on the other side of the Earth. It's a spot in the Indian Ocean. And the closest land to there, the closest we've gotten as far as a reception report to that spot is someplace in Indonesia. And it is, gosh, I can't remember off the top of my head how many kilometers it is. But it's out there. So almost as far away as you can get.
Could you talk a little bit about the VLF 60 kilohertz antenna that you use? Do you use a vertical with a system of radials, or?
Right. Yes, I'd be happy to. So you saw in the presentation WWVB and WWVL. VL was terminated in 1972. It just didn't have the users that justified the budget for it. But WWVB then, what we did was actually configure the two antennas. They're very similar to work together for one 60 kilohertz broadcast. So we have one signal feeding two transmitters, feeding two antennas. And together those two antennas form a type of array, and they're actually quite efficient, pushing 70% efficient for LF, which is pretty remarkable. They are an old design. They were designed, you can look in reference book from the 1920s and you'll see designs that look like that. They are made up of roughly 400-foot vertical element. We call it a dog leg, actually, but it's a radiating element that's suspended in the middle of a diamond-shaped horizontal array of wires. And I'd be happy to talk more with you about that after the presentation. But yeah, that's just a brief outline.
As someone who's new to radio, especially as a ham, what's with the pressurization of the lines?
Yes, good question. Those lines, as I mentioned, are essentially hollow, and they have RF energy flowing through them. Some of our transmitter outputs are 10 kilowatts, and that's average, so the peaks can go even higher than that. If water gets in there, it can cause corrosion, it could cause arcing. And so even if we have a leak, we don't want water to get in. We want the air pressure inside that line to be such that if a leak develops, air blows out rather than water coming in. And we can monitor the air pressure in those lines by, and that's how we can tell if we have an issue.
There is a question we got from the internet. Somebody was asking, can you talk about the 25 megahertz experiment that you're doing?
Yes, 25 megahertz was brought back in service. I believe it was 2014, and it was taken out of service. Originally, the transmitters that we had at the time were becoming more difficult to maintain. Our staffing was low, and it was decided to take that broadcast offline. But we were able to bring it back with the newer transmitters that you saw here, the Collins transmitters, and it is essentially the same, certainly the same quality, the same accuracy, the same timing accuracy and frequency accuracy as any of our other broadcasts. The only difference is it does not have a standby transmitter. And so if we have to take that broadcast down for servicing, we're basically off the air. If we're going to be down for quite a while, we can bring up a standby transmitter at that frequency. But it's a manual operation and it takes some time. Yes, sir. It is. WWVH, the voice that you hear is a woman. Her name is Jane Barbie, and she has passed away now. But she actually provided time of day voice announcements for a lot of different time of day services back in the 50s and 60s. The WWVH, for their timing references and frequency references, they have a smaller version of what we have. They have several cesium clocks that they're compared with a system continuously, or more or less continuously, with the UTC NIST and older. Dave?
So a couple of things. Your first audio, the older one, I'll point out that if the voice was kind of Washington-centric in announcing Eastern Standard Time, the Morse was in the predecessor of Universal Coordinated Time. It was in GMT.
Was it really?
Yeah. I'll further say that if the club is sort of your great fan here, the distributed WWV fan club, of course, is out here. A couple of bits about the scientific views. During the enormous coronal mass ejection a couple of days ago, we record WWV in a variety of ways that we'll talk about next, and then a bit more on Saturday. When that coronal mass ejection got to Earth on the 27th and 28th, we recorded WWV long path. So we got it not just to the antipodes, but all the way around the other way.
So you captured the signal going all the way around the world.
Correct.
Very
in
cool.
Cleveland, Ohio. So it wasn't to Fort Collins and back again, but most of that distance. Additionally, we thank you for getting 25 megahertz back on the air. Our recordings of that during the coronal mass ejection hit on the Earth completely blanked out. I thought our equipment had failed, but it picked up again the next day. And the day after that, there was a sun surface explosion that produced an intense ultraviolet pulse at 1750 on the 28th UTC. And sure enough, right on schedule, my 25 megahertz recordings are blank for about 10 minutes. So it was exactly that, and it was a nice confirmation of all of that event. So we thank you for all that you're doing.
Oh, thank you. Excellent.
Keep 25 on.
Yeah.
Yeah.
So how are we doing on time?
Well, we want to wrap it up. Are there any other questions?
And I can certainly stick around for a few minutes after the next presentation.
Yeah, and we're going to,
Further
after this
questions.
last question, we'll take a 10-minute break, and then we'll be ready to get going.
So regarding the GPS common view system you mentioned earlier, are you saying that there's basically two sources of truth here, where you have WWV and then GPS? And if so, who synchronizes off of who?
Yeah, I would like to meet with you after this discussion. After this meeting, we'll talk more about that. Maybe get one of my colleagues here to help me with it too. But essentially, NIST does not use USNO's frequency as a frequency reference directly. We use just as a timing, a common view timing point to compare our two systems at the same instant. And I'll go and I'll be happy to share more about that. You bet.
Thank you, Glenn, so much for giving us a tour of WWV
Thank you.
and the history of WWV standard frequency broadcasts. So we're going to take a little break, and you can stretch your legs, but we'll be back. Let's do it in 10 minutes, and that should keep us on time. It's PowerPoint. So, okay. And then the
issue is we didn't realize that we weren't going to have a laptop. We had all of our element in Google Drive.
Do you want to do it from up there?
I hate not to be able to address the crowd. Oh, the point.
No, it's just because it.
No, I understand.
It's,
This is migrated material. No, I mean it. This is bad.
well, it works for so people can see you, and you can see to hear. Yeah.
So, I
That's
mean,
what it is.
there's nothing you can do about
Yeah.
it. So, if the slides don't work well,
They will.
have a laptop. Okay. If
We'll
there's
make it
any
work.
problem, we'll keep talking and we'll see if we can get a laptop up to the booth and get the slides.
You don't think they're going to work?
there. Well, it's a translation from Google Drive to PowerPoint, so I may lose some of our material.
Okay.
So
I know what
if
you're
there's
saying.
anything wrong,
Yeah.
we'll get a laptop up there.
I don't know if you can plug a laptop in right up there or not. Oh, I will.
Thank you.
Did they? What was the second standard at the time? Was it really based? I think it was based on speed of light. Like one over 300 million.
Well, welcome back, everybody. Hopefully everybody's working their way back in, and suddenly they'll hear voices and they'll say, wait, I've got to get to my seat. 4 years ago, I had the pleasure of meeting and working with Dr. David Kasdan on the 100th anniversary of WWV, and you heard about that from Glenn's talk. While most of us were focused on a special event station and operating for 5 days straight, and that was 120 hours of operation all night long, it was a lot of fun. David and his students coordinated the Festival of Frequency Measurement, a crowdsourced effort to simultaneously observe and monitor WWV across the country. Tonight, we'll hear where that effort has progressed since 2019 and hopefully learn a little ionospheric science as well. Dr. David Kasdan is an Associate Electrical Engineering Professor at Case Western Reserve University in Cleveland, Ohio. He has incorporated amateur radio into his curriculum and licenses his new students as part of their studies. His science background is extensive, and started as a teenager or even younger, maybe, I don't know, getting into ham radio. His call is 88Y. Rachel Bodecker is a PhD student at Case Western Reserve University. Her call is up there, AC8XY, and she is studying, you're working on your doctorate in mathematics, is that correct? Applied mathematics. And so we welcome her. This is the first time I've had a chance to meet Rachel face to face. We've been talking on Zoom calls for the last year or so. So it's really neat to have her here. And we also have Aidan Monterre, who is an electrical engineering alumni of both Case Western Reserve and our 2019 100th Centennial event with the Festival of Frequency Measurement. She was involved with the HamSCI as a student and now is a member of the NIST Time and Frequency Division at the Boulder Lab. We were really excited she got hired. Her call sign is KB3UMD, which is up there behind me. We welcome her back to Fort Collins. Together they represent the group HamSCI. So please welcome David, Rachel, and Aidan.
Welcome to high tech.
Well, I've got this.
There's
Sorry. Where do I point the thing?
No, you're good. You can start clicking now. Maybe.
Excellent. Greetings, everybody. So, yes, WWV holds a special place in my heart because it is not only my favorite radio station, but it is also what brought me out here to Colorado, working in the Time and Frequency Division at NIST. If it weren't for WWV and folks like David and Rachel and Dave Swartz, I might not be here. So this station holds a special place in my heart. But today we're going to talk about WWV and citizen science. So before we do that, I want to put WWV in a bit of context. We had some questions about how WWV relates to like other sources of time. So I wanted to put WWV in context of the other time and frequency services in NIST. So this is kind of a busy slide, and it's a little hard to see when it's projected at not right angles. But here we have the Boulder, Hawaii, Gaithersburg, and Fort Collins campuses of NIST. And we have a variety of NIST time and frequency services. So down here is WWV and WWVB, which we're talking about today. And so people were asking where we get time for that. So as Glenn mentioned, WWV's time comes from a local time scale, which is a collection of 5 season clocks on the site of WWV. That is compared with our main time scale back in Boulder. And we do that using common view GPS measurements. We also do that with other kinds of measurements. I've actually been working on a project to use digital television of all things to make time and frequency comparisons. So when Glenn said it's not the fact that it's GPS, it's just the fact that it's common, really it is anything in common. If you were to stand on a mountaintop blinking a light, we could figure out how to use that for common view. But you might not want to stand there for that long. So our primary time scale is in NIST Boulder. And the point I want to highlight here is that one, this time scale is the ultimate source of time for a variety of NIST services that have expanded from just things like the radio station to time.gov, which is a website you can go to on your phones afterwards and get NIST time, to our new services like time over fiber and time over satellite services that are being developed right now for increased accuracy and stability, as well as powering all the new fancy research that goes on at NIST in Boulder and in Gaithersburg. But then I also want to say that those same common view observations that we use to compare and sync our WWV timescale with the primary timescale is also what we use to compare with other national labs. We do both more GNSS or GPS common view observations. We also do two-way active links over satellite, and together with the other international labs, we all contribute to this organization called the BIPM, and we coordinate time. And so that is how your time that's coming out of the radio station in Fort Collins gets linked to the same definition of time used around the world. For those of you who are asking about the Naval Observatory, one of those other national labs is the Naval Observatory. So we do comparisons between our clock ensemble and theirs, and they contribute to UTC as well. And so now that so I wanted to highlight that as just the place of WWV in all of these other time services and how that links back to the international definitions so that we all know what time it is. And with that, we will return to the cake, and I will hand it over to David.
Thank you. And I want to thank you very much. It is really utterly, sorry? Oh, microphone, sorry. This is where the camera's pointed, so I'm supposed to stay here. It is.
You can use this if you want to walk.
Well, except the camera's here, so
Yeah.
I'll give you that back. You know, good times always begin with a cake, what can I say? And thank you so much to Andrew for tending after this one. It's really an honor to be here with everyone, to be celebrating such an extraordinary, all but unique on Earth facility as WWV. It really is my favorite radio station, both directly and indirectly. I like classical music. Cleveland has a really exceptional full-time classical radio station. It started as a commercial station in the 60s. And George Settle, the director of the Cleveland Orchestra, who had an utterly golden ear, used to occasionally telephone the station, you know, your turntables are off speed. Because he could hear it. So WWV keeps everybody honest. And I realize we're among friends here, except for one skeptic who thinks that it should all be replaced by GPS. Part of our discussion here is that it really shouldn't. So we did have NerdFest in 2019, and honestly, you don't know what living is until you've partied with a lot of time and frequency freaks. But it was a great time, and today we celebrate the heartbeat of the electromagnetic spectrum, the second tick of WWV. This is the board of incoming QSL cards. Glenn showed the outgoing ones, but these are the incoming ones. And I'll point out, how does the laser, oh, there it is. This is the Case Amateur Radio Club, so this is from where we show all of our first-year electrical engineering students what shortwave radio is, and of course, first light of shortwave radio must be WWV. What else is it going to be? So this is the card of thank you notes, if not perhaps love letters to WWV, and even through the darkness here I can see Matt blushing. He's told me tales of some of the communications that he does get from users, and there are many, many of them, and they're all over the place. Some of them are just hearing First Light on shortwave radio and getting some of their elementary school science education. Some are doing stuff what we do. When WWV was being threatened with defunding, we did a literature search, checked how much NSF, National Science Foundation funded work, was using the signals from WWV, and it was in the hundreds. So we'll talk about a little bit of it, a little bit of the history of that sort of use of it. Even before the time tick frequency standards were in use, when radio was just barely coming of age in the earliest days of active elements, of vacuum tubes, the radio group, the Bureau of Standards Radio Laboratory, already was pondering who might be using this. And for our purposes right now, I want to point out the level of emphasis that was given to students, to individuals who were doing radio experimentation in their backyards and their basements, and already to licensed amateur radio operators. The Department of Commerce, before there was a Federal Communications Commission, was already licensing amateur radio operators, and amateur radio operators needed their own set of standards. The constitutional mandate to Congress that created the National Bureau of Standards, though, is for regulation of weights and measures as used in commerce. So all of these things in mature state are available, but where did some of them come from? And by the way, if you've never heard it, do make a point of, for a good time there. Yeah, okay. So what do you use this for? It's really great that NIST runs these atomic clocks, provides the international definition of time, which Aidan and others can address better than I can, but the second has a strict definition in Système International, and NIST, we should all be proud to say, is our keeper of that. All right, so they're the keeper of the atomic clock. They get to look at the cesium capsule and at the rubidium capsule and its nice red glow. But what do you actually do with it? So there's some obvious things. You set your clock, okay, and Matt had made up bumper stickers. I set my clocks to WWV. I forgot to bring one with me, but it's very nice. All of those clocks, those wall clocks that you can get at Walmart that were described, they are labeled atomic clocks. So they're atomic clocks in the sense that by radio they are linked to the atomic clocks in Boulder. There we go. Tune your violin. Yeah, all right, so here's an interesting one. Tune your violin manufacturers. Tune your violin manufacturers. So violins, quick poll, who plays musical instrument? Yeah, of course, every ham plays something. Who are the string players? Strings. Okay, got some strings. And woodwinds? Yeah, us too. And brasses. Brasses, Dave is back there. Good, okay. Who needs frequency standards? The string players don't. String players don't. You can tune your violin pretty well over a remarkable frequency range. Who needs it is the manufacturers of the wind instruments. And a fascinating introductory history of all of this, I'm supposed to keep on schedule, so I will, is the 19th century effort in Western Europe and in the United States to provide frequency standards for musical instrument manufacturers so that they could unify their construction of instruments and improve international trade in musical instruments and of tuning of orchestras throughout the world. We will talk about that more on Saturday. It's its own universe, but that function of the A440 audio tone transmitted is part of the constitutional mandate to Congress to look after measures used in trade. The trade here is musical instruments. Well, that's obvious. There's this extraordinary paper from 2013. These second ticks from WWV mimic the pulses that come off of a radar transmitter, like at an airport. The second ticks look like radar pulses. Wow, okay, let's try it. Somebody did, and somebody realized you can image ships in the Pacific with the second ticks coming off WWV. We are anxious to try this at CASE, see if we can image our friends on the engineering quad or something like that. And finally, another sort of unlikely sounding use of it is measurements of the ionosphere. Measurements of the ionosphere. That's us, that's HamSCI. Who's HamSCI? Well, we are, and I hope that by the end of this, all of you will want to be also. There's a lot more to it than signing up for the mailing list, so come join us, hang out with HamSCI. We have been appointed here to represent all of the upper end of amateur science in service to professional science. HamSCI is a somewhat loosely organized group that has an annual scientific conference, has weekly meetings, is setting up actually to do manufacturing of electronic instruments that are tied to WWV for some of these measurements. Let me give you a quick taxonomy here. Shortwave radio, it is an old term. I think most of you do know about it. Roughly, it corresponds to the high frequency range, which by definition is 3 to 30 megahertz, which is approximately the range of radio frequencies most amenable to being bounced off the ionosphere and being sent over the horizon that way. Amateur radio, worldwide, except for a couple of countries on Earth, is the licensing system that is kind of loosely managed by the United Nations, actually the International Telecommunications Union, to see to it that the electromagnetic spectrum has areas set aside roughly in the form of national parks for people to be able to do recreational radio, talk to each other, and to do science experimental radio. If you wish to use a national park for observing and sound recording birds, Laura, the XYL, the NFE, that's what they're there for. If you want to be able to transmit radio signals on your own recognizance and study the physics and study the engineering of it, that's what the amateur radio bands are for. And the nations of the Earth coordinate them and provide these together. The ionosphere, if you've seen CATS, you know about the trip to the heaviside layer. So this was theorized about 1895 as an explanation for how radio signals were getting over the horizon. This is before vacuum tubes, before much of anything. And then sure enough, it was identified. There is this thin layer of electron clouds hanging over the atmosphere of the Earth that provides a mirror in the sky for radio waves. And great receivers. That's our manufactured item for studying it. All right. HamSCI, this is us, our fearless leader, Nathaniel Fursell. He started in, before the centennial, about 2016, preparing for the 2017 eclipse. And everyone mark on your calendars, Monday, April 8th, 2024, the great total solar eclipse across the United States. There's not going to be another one until 2049. And we will be measuring the ionosphere with WWV during this. Make sure you're somewhere good for the eclipse. It's a life experience. He got there early, preparing radio experiments for the 2017 eclipse. We had already been measuring WWV with relatively simple receivers that were frequency controlled through the GPS constellation. So the GPS constellation isn't NIST time and frequency, but it's NIST time and frequency traceable because they monitor it. And it provides a remarkably inexpensive, local, highly precise frequency standard to use for seeing what WWV is doing as it actually gets through the ionosphere. At place of launch, it's as accurate almost as any physically measurable thing can be. 10 megahertz with 15 zeros after it. Yeah, I can't do that on my kitchen table. But what I can do is bring 12 zeros after it in with a $100 GPS receiver that's made to do such things. As the signal bounces off the ionosphere, you don't get the direct signal anymore, and the path is changing. The path is changing because the ionosphere gets scraped from underneath by atmospheric weather, and it gets changed from above by solar weather. Here is a rough diagram of the electron clouds over the Earth, over the atmosphere, as they're affected primarily by the sun's ultraviolet plus cosmic rays during the day, and then as the sun sets, cosmic rays at night. The nature of them changes. It's not our discussion right now, except to say that not only does the nature of them change diurnally, it changes with all of these weather systems, weather on the surface of the sun, weather in our atmosphere. So the skip is that bounce of the radio signal from WWV to a receive point somewhere along here. WWV is receivable at more than just one point on Earth because the ionosphere is quite broadly reflective and refractive. But all of these places get affected by how much change is taking place in the length of that path. What we measure is the Doppler shift, and this is where I hand the laser pointer to my colleague Rachel. Here you go.
Put down is next, right? Yes. Okay. All right. So, probably, how many of you have been standing on the sidewalk while a car drove by or an ambulance drove by? Probably a lot. So you're familiar with sound Doppler effect in physical ways. So this kind of, the sound coming towards you sounds like it's higher frequency and going away sounds like it's a lower frequency. Similar things happen in the electromagnetic spectrum. You get Doppler shift caused by the changing height of the ionosphere, right? Because if the ionosphere, if the height on the ionosphere is taller, right? If it's at a greater perceived height, then you've got a longer signal path. It's very strange. Than if you have a lower ionospheric height. And so that longer signal path means that the signal is traveling for longer, it's propagating for longer, and that's going to cause Doppler effect, right? So as the signal, as the height increases, the signal seems to decrease in frequency or redshift, and the opposite happens as the path length path length decreases and the atmosphere height lowers. Okay. This is a little bit weird to look at from here, I'm not gonna lie. So first, we'll talk a little bit about WWV as a signal law opportunity, because in order for this to be useful, right, you might know hypothetically that on your amateur radio station, if you're sitting and listening in your shack, that you're not perceiving the signal as it was sent, right? You might know that it's going through the atmosphere and it's picking up distortion, and it might take a little bit longer than you hypothetically think it would, or if you did a quick calculation, you might estimate. But it doesn't really do you a lot of good unless you have a very precise signal at a very precise frequency, right? So since WWV is so precise, has got this precise frequency that it's going out on, then the Doppler shift is really meaningful if you're listening to WWV, right? Because you know exactly what frequency it's being sent out on. And it's a national standard. And we've got a nice picture here that was drawn at the AGU conference on the whiteboard. Right, so in general, we like WWV, we like monitoring it. HamSCI uses it quite a bit, and we have distributed systems. And we're building a further distributed system to listen to those ionospheric distortions. Okay, and this isn't necessarily a fully new idea. So this is some data from 1957 that's doing a very similar thing, right? So they're listening to some, to a frequency standard, the same way we would. And here's more modern data from 5 megahertz WWV. So you've got laser signal here, and then you have splitting between the E layer reflection from the ionospheric E layer and the ionospheric F layer. So just like in that picture before, the ionosphere breaks up away into different layers, and you can actually see that layer breakdown in the signals recorded by WWV. So you can see the ionospheric height and make estimates of that, and you can also see mode splitting and different ionospheric layer propagation just from the WWV signal, and a relatively inexpensive receiving setup, which is pretty phenomenal, scientifically speaking. Another thing you can do with WWV, or that we have done, before I get into a little bit more about monitoring the ionosphere just outright, is increasing that signal use. So right now it's sending out a whole wheel of potential stuff, including the 440 hertz to tune your flutes on specifically, and second ticks and things. But you can also add potentially more signals that would be useful to scientific researchers and recreational listeners. So this is a signal that was put together by Christina Collins at Case Western and got implemented at WWV, if I can get this to play. Oh, not quite.
That part we didn't test.
Okay, is this the...
Hold on.
I was going to ask, is this the PowerPoint?
At the tone, 22 hours, 8 minutes, Coordinated Universal Time.
Follows is a scientific modulation test. For more information, visit hamsci.org/WWV.
add more, now, without disrupting too much of WWV's current use, you can add a lot of usability, usability to that signal by adding things like patterns and pseudorandom noise and chirps and things, which can be really, really useful. Okay. Oh, let's get back to here. In terms of just using the signal as is, with just recordings from the WWV to look at ionosphere kite, and I'll try to stay on time, we have the Personal Space Weather Station project, which started at HamSCI years ago, probably maybe 3, 4, 5 years ago. When I was an undergrad, so long ago. The Personal Space Weather Station started up. We wanted to have a way for any individual, like an amateur radio operator or an interested shortwave listener, to be able to listen to WWV and record scientific data. So we wanted to crowdsource the problem. And this is really useful because, as an idea, because scientific measurements of the ionosphere are usually really expensive, and they're located in one place. We love our friends at MIT HamSCI, and they have some phenomenal equipment, but it is very expensive, extremely large equipment that takes a lot to keep running and is monitoring the atmosphere in a very specific location in West Bank, Massachusetts. So, or West Ford, Massachusetts. So you have some very nice equipment there, but you can't distribute it over the entire continental United States. It's just not feasible to build, an atmospheric sounder every 100 miles or so. It would be fun, but probably not feasible. So the Personal Space Weather Station, which has parts in Scranton, Case, at MIT HamSCI, it's funded by NSF grants, and there's also TAPR, any TAPR members here? Which is another amateur radio group, the Tuscan Amateur Packet Radio Group. Wanted to build a personal space weather station that you could use in a distributed network. So the main crux of this would be to have some kind of disciplined oscillator, right? Because if you're receiving a really precise signal and you want to see how that precise signal is deviating, you need to be able to compare it in a precise way. Luckily, this has been enabled by technology advancing. So maybe 10 years ago, it wouldn't have been possible to put together a really cheap GPS disciplined oscillator that you could just distribute over the United States. But technology now means that we could for about $300 for Grape 1, build a bunch of GNS disciplined oscillators that are listening to WWV and telling us what that Doppler shift is. Okay. Let's see. That's the main part of Grape. There are some also ground magnetometers built in on the HamSCI network, but the Grape project that Case is involved in mostly focuses on the inexpensive receiver side. Okay, so the Grape Personal Space Weather Station is built to monitor Doppler shift. The Grape 1 is around $300, so it's relatively inexpensive for scientific equipment, especially. And there's a Grape 2 in the works as well. So this is data recorded from the 2017 eclipse that somebody was monitoring WWV, and as that eclipse started, you saw something that looked a lot like diurnal variation or day-night change in the ionosphere and in the signal. You see the Doppler shift change suddenly here, and you see it again at maximum when the eclipse starts to fade, and then here we return sometime night. Worth mentioning also is the Tuscan Amateur Radio Groups, or Packet Radio Groups, TAPRs. They're building an SDR-based system. You can also get on the mailing list for that. And both Grape and Tangerine SDR have weekly Zoom meetings, which you're all free and welcome to come join us on. So they're completely open. HamSCI, anyone can join HamSCI, you just need to join the mailing list. So they also meet on Mondays, and you can join up with that. It is SDR based, and it's also in the works, or I should say software defined radio based. GRAPE is the version that CASE focuses on. GRAPE 2 is going to be monitoring fingers crossed, 3 HF channels simultaneously, targeting the 2024 eclipse and hopefully the 2023 eclipse, if we can get everything deployed on time. Fingers crossed. And so this is the primary network that we're hoping to distribute to measure the Doppler shift. GRAPE is a very appropriate name. It works better when there's a lot of them, and we hope it will ferment into something quite nice. Okay, and here's an example of GRAPE data from John Gibbons. He's in Macedonia, which is near Cleveland, and he's been recording the longest, basically, on the GRAPE system. Hereabouts you can tell when he got a new antenna, which is kind of nice, at his ham shack. But you can really see this kind of day-night variation and this shift, right? Which is very cool. So you can, let's see, point out that we've got local time over here, and this is just dates. So it goes from start of day, end of day, up and down.
May I say a word on this slide?
Oh,
because
sure.
I'm part of this collection project, so let me clarify a few things here. This is about a year and a half worth of data,
Yeah.
and let me take the laser pointer. Thank you. Good. So, beginning of UTC day, which what in Cleveland right now is 7 EST, so here it's 5 EST, ticking along to the end of that day. So 24-hour period here, and we start about the fall equinox here, go through the solstice, go through the spring equinox, go through the solstice, and another cycle of it. And what's interesting about this, this is the climate of space weather. It's not the day-to-day weather, but the climate of space weather is that the frequency shifts occur pretty much as predicted. If you look at our scale on the right, the blue is a positive frequency shift, meaning the path length of the signal from Fort Collins to Cleveland is shortening during that time. The ionosphere is coming down as the sun's ultraviolet creates it at sunup. In the evening, the opposite is happening. The parts of the ionosphere that are supported by the sun are dissolving. The path length is getting longer because those are the low parts. And there is a Doppler shift in the opposite direction. The frequency is coming down. It is maybe more reassuring than anything else that this shape is taking place. But additionally interesting is seeing the day-by-day recordings, seeing how daily solar weather as correlated with the stereo system of sun-observing satellites and other sun observation systems works out. So this is the personal space weather system. We're able to have this enormously distributed system, about 150 stations now worldwide, for an amount of money that people can actually do this. Okay, thanks.
All right. So measuring ionospheric disturbances, now we have this, so hypothetically we built this great network, distributed receivers, and we can measure WWV. What do we do with that? Why do we care? Well, there's the day-night variation, which you just saw, right? We know that the ionospheric height changes over the course of the day-night cycle. Solar flares will also cause a sudden ionospheric change, right? So as the Earth is irradiated with solar energy, all of those particles in the atmosphere become ionized, our ionosphere changes, right? So a solar flare creates a really rapid change to the ionosphere. We've got geomagnetic storms create a really rapid change. There's one change in particular that's really cool because it creates a very particular, orderly, and predictable change in the ionosphere, in which I mean that we can tell when it's going to happen, and we can kind of assume that nothing else major is happening during that time. Fingers crossed, that would lead us to think that the data is doing something else, or that something else might be the cause of our data. So a solar eclipse, gives us a really nice option, for kind of a control situation. So I already highlighted some solar eclipse data from 2017, but in general, if we're measuring WWV through the solar eclipse, then we might be able to go start, figuring out how the eclipse will affect things like HF communications, how large the disturbances will be to the atmosphere, how similar the effects of the eclipse are to that day-night cycle that we see. Would it be like a sudden onset of day and a sudden onset of night? Would it be symmetric, right? And how long will these kinds of effects last? Will it just be during the eclipse, or will there be some lingering effects or asymmetries? Oops. Okay, so in general, a total solar eclipse is relatively rare. There was one of the United States in 2017. There'll be one in 2024. Cleveland will be in the path of totality, which we love. And it will provide this excellent opportunity to block out, basically all of the solar radiation. Well, not all of the solar radiation, but a very, very large chunk of the solar radiation in a confined event that's happening on basically the universe's schedule. So here's the the 2017 eclipse data, again, highlighting this curve here where the eclipse comes in. And again, you can see that sudden onset of Doppler shift. This is a normal 24-hour period used as a control, and this is where your Doppler shift happens. But during the eclipse, you have that sudden offset of the Doppler shift and that sudden offset back as well. Before continuing as planned. So we had kind of a proof of concept in 2017 that WWV could be used for this kind of really real-time, especially since MIT Haystack unfortunately won't be in the path of totality. It'll be very, very useful to have this distributed network up to be looking real-time at the WWV signal. So the great project in general, we are interested in dawn and dusk ionospheric variability during the time season. So even not during the eclipse, we're still hopefully leaving this great network up as much of the time as we can, so we can really be getting a good feel for what the daytime variation is, what the seasonal change is, and things like that. And if there is an eclipse, is it going to be responding symmetrically? How similar is an eclipse to this day-night passage that we've already observed? And could we continue to observe that multi-path splitting, so that F layer and E layer separation in the post-eclipse type world? And then also would the responses be different for two different eclipses? So, fingers crossed, we have the great network up to observe the 2023 eclipse, then we'll have data to compare with the 2024 eclipse. So we'll be able to get a better grasp on the eclipse science and also on ionospheric science in general, because we'll basically be running, multiple very controlled experiments brought to us courtesy of the universe, relatively close to each other with the same network of receivers. Okay, and then there's also a bevy of other ham radio activities during the solar eclipse. So did anyone here participate in the 2017 QSO party? Any hams remember that? Okay. So we had people measuring signal strength, measuring WWV. We also had a lot of people working in a QSO party, so making as many contacts as possible, so we could look at the links formed between places and see what the ionospheric propagation was like real time during the eclipse. So there was a lot of really cool work for that, and it helped confirm a lot of real science that was being done on, very expensive, nice machines in labs. Oh, there was another video here. Would it be, will that play in line, or?
Nope, we'll get it.
Okay, thank you. So these are atmospheric bow waves caused by the 2017 solar eclipse, which is really cool to see. If you
Can you play it again?
if you could play it
Right
one more
now,
time.
let's get a closer look.
Maybe some of that later, but there we go. Yeah, so you can see this is the eclipse path moving through, and then you have these very distinct bow waves being caused in the ionosphere by the eclipse, which is pretty cool. Now this was done by MIT Haystack. I'll have to wait. If we could go back to the slides, I would appreciate it. Thank you. Okay. So yeah, so this was done, but we had a lot of data from there, and it helped to kind of verify the other scientific results and things. And with the distributed grape network receivers, we'll have stuff where we're recording WWV with disciplined oscillators in a distributed network. So these are the two eclipses that we are most interested in. I don't think Cleveland will be in totality again for another 70 years or so. So we really need to get our data. If WWV could keep running perfectly. So the first one coming up is in October, that's 2023. And it's coming just, totality will hit just on the southern end of this state. So for those of you who are local, it's a pretty short hop. Well, okay. It's a little bit of a drive to be in totality, but it'd be worth it. And then the total solar eclipse that's happening, and this is an annular solar eclipse, and then we have a total solar eclipse happening in 2024 in April. And the totality will pass through Cleveland. Okay. It's a little bit of a plug. For those of you who are local, the one that's coming up is very, very close. This is the edge of Colorado. You probably could drive that.
Come join us.
Yes.
Bring your radios.
Yes. Aiden will be there. You should be too. Okay. And the Eclipse QSO party will be happening again in 2023. So, for those of you who didn't do it the last time, that's okay. You have another chance. The universe is granted you this. If you have a ham radio, if you have a station at home, you should be making contacts during the eclipse. If you don't have a station at home, what are you doing? Go get a station at home, make contacts during the eclipse. And if you're a shortwave listener, especially, if you're in a good position from WWV, record WWV. It's our ultimate scientific tool that's just being broadcast out to all of us for free all the time. Okay, and if you want to learn more, join us this Saturday, absolutely. HamSCI is a mailing list. So join the mailing list. You're welcome to join at the Grape or Tangerine SDR working group meetings and WWV. They're around. They have an email, so does NIST. They're really close to us now. So what?
You forgot one.
Oh, and if you'd like to contact us.
The WWV Amateur Radio Club, too.
Oh, yes.
We forgot.
Yeah. Well,
sorry.
Conformal mappings and all that. Yes. So, actually, I still haven't found it.
No, it's not there.
Oh,
We forgot.
yes. Sorry. Sorry about that. That's our bad. But they organized this event, so you probably have their contact information. Just a hunch. And then you can contact any of us as well if you have any questions. And there are some references available also, if you're interested. For the most part, we're really good at contacts. And does anyone have any questions? I believe we're finishing just a little bit over time.
If you have a question for the HamSCI group here, make sure you can get the microphone from me.
I think this question is for Rachel. Do you have monitoring, if I may call them frozen grapes, at the poles? And what happens at the poles?
I don't think we do.
We tried.
Would you like to go to a pole and take a grape with you?
we actually had one packaged to deploy at McMurdo. That trip didn't work out. We're still trying.
So if anyone's going to the Arctic or Antarctic in the near future,
we're trying.
All right. Any other questions? Yeah.
So there are 6 frequencies broadcast by WWV. Are they all? Do you use them all the same level, or are any of them more useful than others?
You have a station.
Yeah, I sent an email to Matt. This must be about a year ago. Upton Sinclair's novel about the Chicago meatpacking industry, The Jungle. The narrator marveled that the industry used every part of the pig except the squeal. We use the squeal. Yeah, we monitor every scrap of the RF that comes out of your antennas. That's right. So everybody who's here from NIST, and especially the WWV crew, thanks. This is really something special.
And which ones do you get the best across the whole network of great receivers, or can you get all of them?
Well, we do get all of them, so you have to take best in what sense. They all provide different data. For example, in that ultraviolet ejection UTC afternoon 2 days ago, I'm monitoring at my home 2.5 megahertz and 10 megahertz in amplitude and Doppler shift, and I'm measuring 25 megahertz in amplitude and time of flight. And all of them show different things, but the times all correlated. It must have been from that event.
Any other questions? How does one acquire a grape?
Okay, that's a little bit of a complicated question. I don't know.
The really short answer is send a note to HamSCI,
Yes.
and let's get you started.
Yes, send a note to HamSCI. Grape 2s aren't out yet.
They're not, but Grape 1s are
Grape 1
available,
are.
and alternative ways of being involved even with your own shortwave receiver.
The other interesting thing is you don't have to be a ham radio operator.
This doesn't involve transmitting.
Yeah.
You don't need a radio license.
All you have to do is receive.
So for whatever reason you don't want an amateur radio license, you can still do this.
But everybody should have an amateur radio license, right?
Other questions? Tristan, here you go.
Thanks. What's your current distribution of grape receivers around the country or the world? Are there any spots within the Arctic that you would really like to see some get deployed?
Do you have the map?
Well, no, I'd have to pull it up, but it'd be on here anyway, so I couldn't.
Do you wish to answer?
Well, I don't have a map.
Okay, the short. I can tell you where
we
really need help. It's Africa.
Oh, that's fair.
We are pretty well populated in the United States, roughly correlating with population density across the country. We would like a reference station next to WWVH on the western side of Kauai. That one's been difficult. We're pretty well represented in Europe. We're pretty well represented across Canada. The problem is Central Africa, and we have some, perhaps Maxwell, do you want to say a word about our contacts in Africa?
Oh, I'm trying to get one in oh, yeah. So I'm trying to get a grade in Burundi right now. That's in Central Africa, but that's still a work in progress.
Does that answer your question? Where we need them?
Yeah.
Oh. I guess one thing to add, and it might sound a bit trite perhaps, but some of those maps we showed with numerous points, really every bit of data does help, and so for some of the things, the more density of stations we have, the prettier picture we get to look at the end of the day. And so it is kind of, in some sense, a numbers game. And so wherever your station may be, we'd like to see it.
That's certainly true. I'm going to add one more thing occurred to me. We're trying to populate a couple of great circle paths with receivers. We need one in central Iowa, if anyone can help with that. That's so the issue there is that it's along the Great Circle Path from WWV to Cleveland, where much of this started, and it's at the approximate point of the first ionospheric bounds. So we need one in Iowa, one near Chicago, which we have, I forgot exactly where the other one is, but around Ames, Iowa would be useful. And then for a north-south, and extending that Great Circle line, we'd like one around San Francisco. We are underrepresented in California, oddly. So we would like to fill in that. And then a north-south path, we have some Texas stations, and we'd like ones north of WWV along that Great Circle. So again, if anybody can help out, but every datum helps to get your receivers warmed up and get those files mailed.
Rachel, you mentioned that the eclipse in 2024 is going over Cleveland, but don't you want the receiver to be your receiver in Cleveland, you would actually want the eclipse to be midpoint between Cleveland and Fort Collins.
Right, I was mostly making that point because it would be very exciting for us Cleveland people. But the nice thing about having a distributed network, right? So MIT Haystack isn't in totality for the eclipse. Well, they're not going to pack up that radar and to move it anywhere. It took a lot of work to get a lot of those machines in where they are. So we don't have to worry about moving anything. We just need to worry about distributing receivers to people who are already interested in receivers.
One of our sweet spots for the eclipse that happens to be at just the right spot across the eclipse path from here, from WWV, is the Atlantic coast of Florida. So if anyone is able to set up shop on the Atlantic coast of Florida for some period of time before that, during the eclipse, and some period of time after, that certainly would be a help. We may wind up driving some equipment there ourselves. University of Florida at Gainesville is well positioned, and we're working on it.
Okay, so you spoke a lot about Doppler shifts, and at the same time you're saying time of flight measurements, right? So obviously the signal has an absolute time encoded. Now, I was just wondering, this, particularly given that there's more stations, like until now the DCF from PTB in Germany, I wonder, you could probably build a poor man's GPS type thing out of these, right? Have people tried this?
You're exactly correct. It's like reconstructing the LORAN system, really. It would be a hyperbolic navigation structure, and actually even between WWV and WWVH, that's at least an interesting demonstration trick, if not of maybe first-rate scientific value. But yes, you're certainly correct. The time of flight measurements are interesting. I invite you, I don't want to get into it right now, but I invite you to look up our work in coherent CW, in GPS timing controlled radio telegraphy. So we get to reconstruct 1820s telegraphy into an NIST traceable form, so that amateur radio operators, just for the joy of making contact with each other, get to make time of flight measurements and report them into central database. We got cool stuff going on. That one's not really WWV strictly, but it is NIST.
Any other questions? This is all very interesting to the nerds present. Does it have any practical application?
Oh, practical of knowing what your atmosphere is doing during a solar event. Like
Let's start with one word, one term, the Carrington event.
Yes, that's a pretty big one. So none of you were alive to remember it, but it was the biggest.
I may admit, but
it was the biggest solar flare in solar cycle 10 in recorded history. I mean, what we've recorded. It was at a point in human history in the Victorian era, would be proper, where we had enough technology to notice a solar flare because we had built telegraph stations all over, some of which caught on fire. It was a very bad solar flare and it affected electronics on the Earth. Comparatively now, I would say we have a lot more electronics than a telegraph station. And especially if you're trying to do something like launch a fleet of satellites into the atmosphere, it might be helpful to know what the sun is doing and how the ionosphere might respond to it.
So yes, in the sense of aiding the power grid and the communications infrastructure of the world, knowing when solar storm events are happening, when largest winds of charged particles through large enclosed loops of conductors are happening and may be destructive, yes, we certainly hope to supply practical information for that. Much of our work right now is for the joy of science itself, but yes, we do hope to have practical data to offer.
Would that be useful for airlines as well?
Yes, you know, the airlines are an interesting thing too. Anybody watch Tamitha Scove's podcasts? So Tamitha Scove, look up the Space Weather Woman. She's a fully qualified PhD space weather person. I'm blanking on what the correct word is for that. But her husband is a stand-up comedian and set her up in the persona of the Space Weather Woman. She has a weekly podcast that's rather tongue-in-cheek, but it is authoritative. One of her campaigns for the past several years has been to have notification for airline crew who are above much of the ion absorbing part of the atmosphere for an awful lot of their lives,
and as to space weather and how crews should be scheduled to avoid excess space X-ray exposure. She has not had luck gaining a lot of traction with the Federal Aviation Administration so far. I intersect with her at the American Geophysical Union, and I've been trying to get her to present another group that I'm involved with, the Aerospace Medical Association, and it's been difficult. But yes, the issues are quite real, and this would be part of that.
Yeah, I also forgot to make the obvious point. How many of you are hams?
Everybody.
HF communication is the biggest probably interest to the audience at hand.
And GPS.
GPS as much as it is nice to know what the sun is doing. It's really crucial to know what the sun does to our communication medium, which is the atmosphere. So if you're ever in a situation, I mean, the internet is very nice, but it's primarily a wired connection. So if you're going to do anything wireless truly in this world, and you're going to do it over long distances, you're going to need to know a little bit, or a lot of it, about the ionosphere.
And as long as we've talked about the hyperbolic systems and LORAN and reconstructing LORAN using WWV and WWVH, do the NIST folks have any news to offer about E-LORAN, about the proposed contemporary NIST-controlled LORAN structure to provide backup in the era of GPS spoofing?
It's a proposal to the federal government right now, and there's no updates on whether it will be funded.
But maybe.
Maybe.
Yeah, the ground-based hyperbolic systems really do still have their place, and in some sense we mourn the loss of the LORAN chains.
All right. There's a question on the other side.
I was wondering if any analysis or what has come out of the analysis of the special test signals been transmitted on WWV thus far.
So the test signals are, and we thank WWV for offering us 1 minute of each hour for that. That was carefully designed, but as a first cut for measurement of the dispersivity of the channel, for measurement of the linearity of the transmitters, for measurement of time of flight, for a variety of things. We do not have publishable data from it. This is a preliminary structure that is not accurate to the extent that WWV itself is. The signals are generated accurately in time, but not in phase. They are actually on a compact disc that plays 1 minute out of every, yeah, okay, who said that? So the short answer is no, I don't have data to present yet. The longer answer is this is an ongoing project, and we certainly expect that there will be. Join our club and get involved with it if you like this kind of thing. Okay, you get to answer Liz Donnelly's question.
Have you heard of others around the world who are receiving the chirp who found other uses for it or are using it also? Because everybody's getting it.
The WWV current, or do you mean the test signal?
The test signal, the chirp.
Christina would be the one to ask. So WWV has, the modified signal has its own sort of working group, and the signal is relatively new addition. I don't think we've heard from anyone. We've definitely heard. So the video I showed was somebody who made the recording, who I don't know. So some people who are out there listening to WWV, as one does on a Saturday afternoon, have noticed at this point, as all of us do from time to time, have probably noticed the signal, and some people have made very, very nice recordings of it. But I haven't heard back from anyone doing something with that specific test signal yet.
But Dr. Christina Collins, who in December essentially defended her PhD in amateur radio, it's her work and she may have. So let's get her in touch with you to talk about that one. Yeah, you need to know this. So yes.
Her contact info will absolutely be on HamSCI.com, and actually if you go to HamSCI for /WWV is all the information for the working group.
I'd like to conclude with a round of applause for the NIST and WWV and WWV Amateur Radio Club crowd.
And thank you two for joining me today.
Well, thank you, everybody, and thank you, David and Rachel and Aiden, and we really appreciate everybody coming out tonight. We thought this would be kind of a unique place to do this event, and thank you so much. And all you folks that are catching us on streaming, will edit out the beginning. Thank you.
I'm the only person who didn't write slide notes, just for the
I
point.
didn't.
No, you wrote aggressive slide notes. But I'm just saying
No,
for the-
those were all